Alright, so today we're going to go ahead and get to 1.2, which is the exploration or exploring absolute values. So we're gonna be introducing a new function that was introduced to us in AP grade 11 if you took AP. However, if you didn't, this is probably new to you. So let's go ahead and get started. So an average person's blood pressure is dependent on their age and gender. For example, the average systolic blood pressure (PN) for a 17-year-old girl is about 127 mmHg. The symbol mmHg stands for millimeters of mercury, which is a unit of measure for blood pressure. The average systolic blood pressure for a 17-year-old boy is about 134 millimeters of mercury. When doctors measure blood pressure, they compare the blood pressure to the average blood pressure for people in the same age and gender group. This comparison PD is calculated using the formula P subscript D is equal to the absolute value of P minus PN, where P is the blood pressure reading and PN is the average reading for people in the same age and gender group. So let's go ahead and look at this. How can the blood pressure readings of a group of people be compared? So first we have Jim is a 17-year-old boy whose most recent blood pressure reading was 142 millimeters of mercury. Calculate PD for Jim. So PD, remember, PD is equal to the absolute value of P minus PN. So in our case, we will have PD 142 is equal to the PD is equal to the absolute value of 142 minus 134. So just computing that, you'll get a number of 8, but it's in the absolute value. So the absolute value of 8 is still 8 because it's positive. So right here we'll have 8. Let's go ahead and do B. Joe is a 17-year-old boy whose most recent blood pressure reading was 126. So we use the same formula here. It's the absolute value of 126 minus 134. 126 minus 134. So now you'll realize, wait a second, we got a negative number. It's the absolute value of negative 8. So whenever we have an absolute value of something, we don't care about negative or positive anymore. We ignore the direction and only care about the magnitude. So we only care about this numeric value, which is 8. So the PD is theoretically the same for Jim and Joey. So see, I notice that even though they have different blood pressure reading, their PD is still the same due to the absolute value. Now we're going to go ahead and complete this following table, calculate the PD value for 17-year-old boys, which you should go ahead and complete it yourself, but I have also done it in Desmos just so we can work on it together. So if you want, pause the video right now and give yourself some time to go ahead and do this. Here is what I have done. This is my entire value or table that I have made. And as the question asks, describe these characteristics of graph. So we have to graph this. So which I had here, but I didn't do any regression, so we don't have a graph yet. But we do have a pattern. We have a scatter plot. So let's see. From this graph, we can roughly estimate our domain, range, zeros, or whatever. So look at this. Is there any domain for so what's the domain for our function here? So as we can see, if we expect these to extend all the way on, the domain should be all x values. So domain is x ER. Now let's do the range. So what is the range? So we notice that these go all the way up and they bounce off the x-axis. So at one point it's equal to the x-axis, but besides that point it never comes back. So it's y such that y is all real number but y is greater or equal to 0. Now about zeros. Let's talk about zeros. So zeros, notice that we only have 1 0 here, or if it's slightly above the x-axis, so it's not even the 0, it's 135, this point. But when you have an absolute value of this, so when you have this function right here, what makes it 0? Obviously, inputting 0 will result in 0. So this is our only zeros, and as we notice, it bounces off the x-axis and never comes back. So it means that this is our only 0 point. Since there's no asymptote, as no values put in this absolute value will make our function disappear. So our function is defined fully. So the shape of the graph looks two straight lines. It looks like a linear function. This is our axis. So it looks like this one linear function, but just as the point crosses the x-axis, it got bounced off. Instead of going down, it goes up. It got bounced off the x-axis and goes up now. This is the shape of the graph. Intervals of domain which the function PD are increasing and decreasing. So basically increasing, so let's do the function of absolute value of x. So let's see. So on decreasing, from left of x, it's always going down, and the right is always increasing. So we can say decreasing from negative infinity to 0, and increasing from 0 to positive infinity. And behaviors of the values of the function as p becomes larger. So as p gets extremely large, as p approaches infinity, our y also approaches infinity. And as p approaches very small, so as p approaches 0, y also approaches 0. It's very straightforward. Now let's go ahead and do this reflecting part. Why might you predict the range of your graph to be greater than or equal to 0? Well, as we see, the function is monotonic after the asymptote. So after the 0. So as it bounces off the x-axis, it only increases or it only decreases. So for the to the left, we notice it will always go up. It will always go up. It always goes up. And for the right, it will always go up as well. So we notice that it will only move in one direction. It will not change direction no matter what. That's why I predict our graph to have a range of greater or equal to 0. So what other function with domain greater than Pn could you have used to plot the right side of my graph? Well, as we can see, this graph, and we don't leave this proximity, we could use a quadratic. Or if you get more creative, we could have used a quartic, because we don't leave this proximity. Or if you're very creative, we could use a sinusoidal function. So there are many other functions with the domain similar, and we could have used as a regression to plot our graph. This all makes sense because we don't leave this proximity. We don't leave here very far. If let's say we had a point of 2000 and then we did 2000 minus 134, that would have been a really huge value up here, which is all the way up here. And then when you have this point and it's extended from the graph, now a quartic or a quadratic no longer makes sense. But because we don't have that point and our points are quite close together, so having these other functions, these other possibilities of a quadratic, a quartic, and a sinusoidal, it still makes sense. How will the graph of y absolute x compare with the graph of this if PD is the y coordinate and P is the x coordinate? So basically we have already worked with the absolute value function, and we do have it over here. It's just bouncing off, pretty simple. Notice that this is the exact same thing, except for this doesn't reach 0. Oh, well, this doesn't reach 135.0. It's 135.1. So the only difference is that this has a different x-axis and it has a different spread. It doesn't have a different x-axis, but it has a different x-intercept and it has a different spread. But besides that, the general shape is always the same. This, because it has this absolute value function, it's always going to be similar because our parent function is the absolute value of x. And here we have a little summary of our lesson today. So the key idea, f of x equals to an absolute value x is the absolute value function. On the number line, this function describes the distance f of x of any number x from the origin. But we need to know something. For the function f of x equals to absolute of x, there's 1, 0 located at the origin. The graph is comprised of two linear function and is defined as follows. F of x equals to x if x is greater or equal to 0. F of x is equal to negative x if x equals to below 0. So notice they can write this, they can express an absolute value function as a piecewise function. And when you come to solve some absolute value function problems, we'll have to use this sooner or later. The graph is symmetric about the y-axis, and as x approaches large positive values, y also approaches large positive values. As x approaches large negative values, y also approaches large negative. Y still approaches large positive values. And the absolute value function has a domain of xer and a range of yer, but y equals or greater than 0. And every input in an absolute value returns an output that is always non-negative. And that is it for today's class. We will be learning properties of graphs and functions.